Hello everyone and welcome back to this lecture series on powder metallurgy. Right now we are on this topic liquid phase sintering, and so far we have discussed about the basic mechanisms, and then we started discussing about the different stages and the different mechanisms which are operative in these stages, right? So in the previous class we talked about the first stage of the densification in this process, and it was through particle rearrangement, which happens due to the capillary force which is exerted by the liquid. So once the liquid forms and the particle surface is weighted by the liquid, a capillary force is developed, and due to that the particles rearrange themselves. So this is what we have seen in the previous class, right? So that's the first stage or the initial stage of densification in the liquid phase sintering process, right? And then we also talked about the liquid redistribution as to how it happens during this rearrangement process and how does it lead to the rearrangement of the particles. That also we have discussed. We have discussed about different types of pores and how they get filled by the liquid as it is redistributed. And then finally we talked about two types of rearrangement. One is primary rearrangement and the other one is secondary rearrangement, right? The primary rearrangement is due to the rearrangement of the main constituent particles due to the capillary action of the liquid, while the secondary rearrangement is because of the penetration of the liquid into the grain boundaries of the particles. So here when the solid-solid surface energy becomes more than the solid-liquid surface energy, the liquid penetrates the grain boundaries as we have discussed before, and as the liquid penetrates, the particles fragment into smaller pieces as you could see from this particular figure over here. And the secondary rearrangement is all about the rearrangement of these fragmented particles. So today we are going to continue on this and see the next stage of the liquid phase sintering process in this particular class. So the next stage of the densification process is solution precipitation, as you can see from this figure once again. So as was discussed before, the small grains dissolve in the liquid and then reprecipitate over the larger grains. The densification in this stage can occur through two modes. One is by contact flattening, and the other mode is through Ostwald ripening. Which is accompanied by the grain coarsening, because in this case the bigger grains grow at the expense of the smaller ones. So let us first talk about the contact flattening mechanism. Here the model which is proposed for the densification mechanism through contact flattening considers two spheres of similar size, as you could see in this figure here. Let's say the radius of the sphere is A. And these two are in contact. So the initial center to center distance is L0. Now the solubility at the contact points is higher compared to other places on the surface of the particles. Okay. So therefore, the mass will be transported away from the contact points, and as a result of that, these two particles will move to each other as the contact points dissolve along the line which connects the center of these two spheres, right? And as that happens, the contact points will get flattened, which you can see from figure B. So let's say due to this center to center approach of these two particles, due to the dissolution of the contact points, let's say each sphere is moved by a distance h. And let's say x is the radius of the circular contact area. Okay. As you can see from here, h and x are related to each other by this equation. H is approximately given by x square by 2a. Okay. And the volume of material which is removed due to this center to center approach is given as pi a h square. Okay. Now let us see what is the diffusion rate through this liquid in this stage. The flux from the boundary per unit thickness J is given as 4 pi dl delta C, where dl is the diffusivity in the liquid and delta C is the concentration difference, where C naught is the concentration at a flat stress-free surface and C is the concentration of the solute atoms at the contact area. And the rate of material removal dV by dt, that is given as delta L into J, where delta L is the thickness of the liquid bridge and replacing J over here we will get dB by dt equal to 4 pi dl delta L delta C. Okay. Delta C is small and can be written as this. Where PE is the total stress on an atom. Omega is the atomic volume, and the other terms have their own meanings, their usual meanings. Now, if the capillary pressure is P, a force balance would give this equation. Where K1 is a geometrical constant and we have seen before that the capillary force P is given as 2 gamma LV by R, where R is the radius of the pore so this capillary pressure is actually due to a spherical pore in the liquid. So now if you substitute P in this equation, then we get PE as this. Now, assuming that the radius of the pore is proportional to the sphere radius, that is R is proportional to A, or if you introduce this constant R equals to K to A, okay, K2 into A, and from there we get PE as this, okay. So from here delta C by C naught can be written in terms of PE. So if we replace PE from here into the delta C by C naught equation, then we will get the following equation. And now if we take dV by dt from here, and replace delta C over here, then we would get dV dt as follows. And we have also seen before that the volume V is given by pi a h square. So from here we would get dV by dt as this. So now if we replace dV by dt over here, then we would get the following expression. And now if we integrate this with the boundary conditions, h equal to 0 at t equal to 0, then we will get an expression for h, And now the shrinkage delta L by L naught is given as H by A which is also equal to this 1/3 delta V by V naught, and therefore the shrinkage is equal to, if we put the value H from here, if we substitute H which we derived just now, then the shrinkage becomes this. So shrinkage varies with 1/3 power of time. So that's the densification, which is basically given by shrinkage. So densification in this mechanism varies with 1/3 power of the sintering time. And you can also see that the densification is inversely proportional to the 4/3 power of the particle size. Right, so which again means that the shrinkage is higher for lower particle sizes, or the densification is higher for lower particle sizes, and the densification also increases with 1/3 power of the thickness of the liquid boundary. So this is when the diffusion through the liquid is the rate controlling mechanism. Right, so these are the parameters which affect the densification in this particular mechanism of solution precipitation. But the mass transport rate can also be controlled by the interface reaction, which leads to dissolution of the solid into the liquid if it is slower. So for the interface controlled mechanism, following a similar approach, it can be shown that the delta L by L naught, that is the shrinkage, is given by the following equation. Where K3 is the reaction rate constant for the interface reaction. So here you can see that shrinkage scales with square root of time, unlike the previous case when it was proportional to 1/3 power of time. Okay, so that was the contact flattening mechanism of densification during the solution precipitation stage of liquid phase sintering. So let us take a moment to summarize this lecture. So to summarize, we can say that there are two modes of densification during the solution precipitation stage. One is by contact flattening and the other one is by Ostwald ripening. Today we have discussed the contact flattening mechanism of densification. Here the particles approach each other along the center line as the contact point between them dissolves due to a compressive capillary stress that works at the contact points. And since the solubility at the contact point is higher compared to that in any other portion of the particle, there is a chemical potential difference, and due to that the mass is transported away from the contact points, and as a result of that the contact points become flattened and the center of the particles approach each other along the line which joins the centers of the two particles, like what you can see over here. So this center to center approach as a result of the dissolution of the contact points leads to a flattened contact area between the particles, right? And this center to center movement, or the extent of movement h, is given by the radius of the contact area and the radius of the particle through this particular equation. Okay. And then we talked about the rate of material removal dV dt, and we have seen it basically depends on the diffusivity, the thickness of the boundary layer or the thickness of the liquid bridge delta L, and of course the concentration, right? And using this two particle model, the kinetics of the process, that is the time dependence of the densification, was derived. And as you know by now, densification is manifested by the shrinkage delta L by L naught, which is given by H by A in this particular case, where H is the center to center movement of the particles due to the dissolution of the contact points between the particles, and A is the radius of the particles. Okay, so first H was derived from the material removal rate dV by dt with an expression like this. Okay, and from that the shrinkage delta L by L naught was derived as H by A, which will ultimately give rise to an expression like this. Okay. So first dV by dt was derived, and from that we derived the shrinkage or the densification, and here we have seen that it varies with 1/3 power of the thickness of the liquid bridge, 1/3 power of the sintering time t, and inversely varies with the 4/3 power of the particle size. Okay. So as the contacts flatten and the material is transported away, shrinkage takes place, and that is how the densification occurs in this case. Okay, so that's all I have for this class today, but I will see you soon again. Thank you for your attention.